we go. This should work out for us. And if you have questions along the way, or particularly if you have questions that come up between now and tomorrow night, email me with the questions so that I can address them directly. Okay. The May 13th session, there's no video. Practice problems, especially multiple linear regression, logistic. Oh, okay. I'll tell you what. I have a better idea of you definitely are going to be responsible, and then you see the lab exam is pretty much directed at a lot of that material, right? Because a lot of that lab exam covers chi-square, relative risk odds ratio, regression, correlation, scatter plots. So we're going to review quite a bit of that right now. And as far as multiple regression, I think since we didn't broach the subject of multiple regression in the lab exam, in class, in the lecture exam, you're not going to have computers, so you're not going to be using SPSS to do calculations. However, it's conceivable that you might get an output, a table that comes from SPSS, and you might be asked to interpret that table. So between either now or tomorrow evening, we'll approach that, how to interpret a table that you might find on the exam. So I think you guys will be prepared for that. Logistic regression is a little bit more out there, a little bit different than what you're used to in reading the tables for linear and multiple regression. So I'll broach that subject tomorrow night. We'll figure out what we need to know about that tomorrow night. So okay, so let me get started on this. I'm going to start with kind of what we saw, a practice version of, say, the final exam, except I'm going to use a completely different data set. Okay, so a couple of things that we asked for on the lab exam was to calculate a relative risk and odds ratio. We started with a description of a situation where I don't remember if I actually gave you the tables or if it was actual a description and you had to fill the tables in. But I'm going to start from these tables that I have displayed right now. Okay, this takes a look at a emergency room input, and it's a survey of motorcycle injuries, emergency room visits due to motorcycle injuries, and it examines how many significant injuries were associated with people that didn't wear a helmet, and how many injuries were associated with people that did wear a helmet. So it's injury and no injury. Let's say that's a head injury. If you're going to an emergency room, you probably have an injury. Everybody has an injury. So let's say that injury refers to head injury. Okay, so we want to know whether people that wore helmets, let's call this bicycle instead of motorcycle, people that wore helmets involved in a bicycle accident that had to go to the emergency room, how many of them had head injuries, how many of them didn't have head injuries. Okay, and we see that within this study group, within this sample, that 90 people weren't wearing helmets and 100 people were wearing helmets, for a total of 190 people. And we find that out of the 90 people that that didn't wear helmets, 24 of them had significant head injuries. And of the 100 people that entered the emergency room over that month, let's say, 19 of them had significant head injuries, even though they wore a helmet. Okay, so totals just come out to 43 out of this total of 190 inputs. 43 of these people had significant head injuries, and 147 of them didn't have significant head injuries. Can anybody tell me what the prevalence is? What the risk of having a head injury overall for this population of 190 people? What would that be? What would be the prevalence? What's the likelihood that any individual within this whole group would have a head injury? Okay, it's early in the morning, so I'm not going to keep you waiting. I won't wait for you to answer that question. Not that hard, right? Okay, it's going to be, the prevalence is 43 people out of over 190 people, right? 22.5% of the people had a head injury. That's the prevalence within this sample or the population that it represents. Okay, so now the table that we see up here is our observed values. Okay, and the table that we see down here that we're about to fill in are our expected values. Okay, so we're still dealing with 90 people and 100 people. We can't change that. The number of people that came in are the number of people that came in. And we also know that 43 people got injured, had significant head injuries. 147 didn't have significant head injuries. Okay, now the thing is, though, we see a difference in the proportion of people that had head injuries depending on whether they wore a helmet or not. Well, this is the real data. This is what we really observed. And we're going to say to ourselves in our expected values, we're going to say out of those 190, out of those expected values, oh, hang on a second here. I just realized why I'm not seeing responses here. Oh, you guys were responding to me and I didn't see it. Thank you very much. Thanks for the reminder at 190, Bill. So we would expect the people that didn't wear a helmet, if there's no, if helmets don't provide any kind of protection, we would expect people that didn't wear a helmet to have head injuries at the same rate as people that did wear a helmet. And we know that overall that rate is 22.5%. Okay, so how many people out of 90 would we expect to have a head injury if you didn't wear a helmet? Well, there's 24 people if in real life, but we would expect that out of 90, 22% of them would have a head injury. So I'm going to just put that into here. Equals 22% times 90. Okay, and how about people that wore helmets? 100 people wore helmets, right? So in that group, I would expect 22% of 100 to have a head injury. And if you add these two together, you'll find that you can wind up to 43. So you're going to that's kind of a check for what you've done. You know that you got the total 43. You did something right there. Okay, so now how about people that didn't have head injuries? Well, since there's 90 people, that's going to be equal to the number of people that, that's going to be equal to 90 minus the number of people that had a head injury. And this is going to be equal to 100 minus the 22 people that had head injuries for that group. Okay, so now at this point, if I just want to keep things nice and neat, I can go up here to cells and formatting, and I could round this off, and I might round it off to 3 decimal places, let's say, to 1 decimal place. Okay, this is 3 significant digits. This is now all 3 significant digits as well. Okay, so that might be a good spot to round it off to. Now, fortunately, in Excel and in your practice, you should probably figure that you don't want to do any rounding until all your calculations are done. Fortunately, in Excel actually saves, even though I've rounded these visually. I changed the formatting around to these visually. As far as Excel is concerned, I'm just going to paste the value here. As far as Excel is concerned, it saves every digit. So even though that number is 20.4 to our I, it's actually saving that entire number. So if we stick with Excel in terms of doing these calculations, our subsequent calculations not going to be suffering from rounding, from building up errors from rounding. Okay, so we really don't want to round till, maybe you could round when you post this in the copy this into your answer sheet or something like that. You round, and I would look towards significant digits, at least the number of significant digits, maybe one more. So the largest number of significant digits here is 3. Right, so I want at least 3 significant digits. Maybe I could have even gone 2 decimal places. So I display it as 4. That would simplify it enough and make it easier to work with, I think. Okay, so now let's take a look at this. We have our observed values and we have our expected values. Well, before I go any further, let's talk about risk of having head injury and odds of having a head injury. Okay, now if I asked you, what's the risk of having a head injury if you didn't wear a helmet among this group of people? Well, there's 90 people, 24 of them had head injuries, so the risk that you're at for a head injury is equal to 24 divided by 90. Simple as can be. Your risk is 27%. Okay, what about the risk if you didn't wear a helmet? That's going to be equal to 19 divided by 100, or 19%. So the risk is higher for people who don't wear helmets than for people who do wear helmets. Another way for us to express that is the odds. Notice I'm only using the observed values here. Another way to express that is to use odds. What's the odds of having a head injury if you didn't wear a helmet? Well, the odds are 24 versus 66, 24 to 66. So your odds are going to be equal to 24 divided by 66, okay, which is 36%. Okay, what about your odds if you did wear a helmet? That's going to be equal to 19 divided by 81. So your odds if you did wear a helmet is 0.2345. Okay, so now we have risk for wearing a helmet, not wearing a helmet, risk for wearing a helmet, odds for wearing a helmet, odds of head injury for wearing a helmet, and odds of head injury if you didn't wear a helmet. So if you were to look at odds from the perspective of what does that mean, odds? Well, if we had out of 100 people, I'm going to make another column here. Out of 100 people, 50 of those people had head injuries, and 50 of them didn't have head injuries out of a total of 100 people, you would say the odds are 50 over 50, or 1 to 1. In other words, the odds of having a head injury are just as good as the odds of not having a head injury. So if this were 75 and this were 25, what would your odds be of having a head injury? Well, 75 over 25 is 3. So your odds of having a head injury are 75 to 25, or 3 to 1, or 3. Okay, so if I go back up here, the difference there is that the risk would be before, when I had 50 and 50, the risk was 50 over 100, or 50%. Just another way of describing the same relationship. Okay, so now I'm going to go back up here to our calculation for risk. The risk if you didn't wear a helmet is 26%. The risk if you did wear a helmet is 19%. The relative risk, how much riskier is it to not wear a helmet? Well, that's going to be equal to the ratio. Anytime you hear relative risk or a risk ratio, anything you hear the word relative or ratio in statistics, you're usually going to divide one number by another. So in this case, you're going to divide the risk of not having a helmet over the risk that you were at if you wore a helmet, and that's going to be 1.4. That's basically telling us that you're 1.4 times as likely to have a head injury if you didn't wear a helmet versus if you did wear a helmet. Similarly, the odds ratio is going to be equal to the odds of having a head injury if you didn't wear a helmet over the odds if you did wear a helmet, and that comes out to 1.55. Both of these are always going to be in the same direction. They're either going to be above 1, below 1, or 1. Okay, so now here's the tricky part. Okay, we know that it's risky. Based on this information, we know that it's riskier to not wear a helmet. And even with odds, we know it's riskier not to wear a helmet. Okay, so now what would you expect the risk to be if there was no difference between wearing a helmet and not wearing a helmet? Well, we already know that. That's the expected values. The expected values tell you are basically you calculating what should this table look like if there's no difference in risk or odds of having a head injury, whether you wore a helmet or not. This is the number of people we would expect to find here, 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 and here. So in other words, our relative risk is going to be equal to 20.4 over 90 divide, and this versus not wearing a helmet is going to be, 20.4 over 90 versus, whoops, let me just put this in here, equals 22.6 over 100. Okay, it's the same. So the relative risk is just going to be the risk for wearing a helmet divided by the risk for not wearing a helmet. It comes out to 1. If there's no difference between wearing a helmet and not wearing a helmet, the relative risk is going to be equal to 1. Similarly, I'm not going to bother to do the calculation, but similarly, the odds ratio would be equal to 1 as well. Okay, so now the fact that we calculated in the real values that the risk was different than 1, larger than 1, and the odds ratio was larger than 1, that tells us that there is a difference in risk. So now next problem is that for starters, we can't get exactly 1 from this table because we can't get a resolution that's the same rate, the same prevalence as the observed table. We can't get it here with whole numbers, and you can only have whole numbers if you're dealing with real people, right? So I can't even really devise a table that would give me exactly 1. And even if there was no difference in risk, I wouldn't expect it to be exactly 1 anyway, because one person mentioned there's no sound. Is my sound back? You guys hear me? Okay, good. Thank you. If I were to calculate this, I would expect my expected value is 1. My expected values for odds ratio relative risk is 1 if there's no difference in risk, right? But even if that were true, just by the nature of random sampling, the random sample I would get during any month of people coming into the OR, I wouldn't expect to get exactly this result, even if there were no difference between wearing a helmet and not wearing a helmet, right? So the question now becomes, how different from 1 does this have to be in order for us to say that this data is good enough for us to say that we really believe that there's no difference? Well, problem there is that we can't tell from this point estimate. Remember, this is 1 number, it's a point estimate. We need to work with a confidence interval. Okay, in a confidence interval, we have to calculate a standard error, we have to calculate a margin of error, we have to add and subtract that from our point estimate, and so on and so forth. Okay, well, fortunately, we learned a lot of stuff about proportions earlier in the semester. We're not going to do that here, but you can see that these are just proportions. And if we're dealing with proportions, we can calculate, with a little work, we can calculate a confidence interval. In other words, we may know this is 1.4, but we may say, okay, it's 1.4, but based on the variability of this data and the sample size, we may find that the confidence interval is actually, say, 1.1 to, and it would be the same below and the same above, so it would be 0.3 above, be 1.7. Okay, so our confidence interval tells the relative risk. Even though we estimate it to be that, we are saying that we're 95% certain that the real confidence interval, the real relative risk for the entire population of everybody that gets into a bicycle accident is 1.1 to 1.7. Let me just put it, boom. Okay, so now what we're trying to prove is that the risk in the real world is different than we would have predicted if there was no difference in risk. Okay, no difference in risk is 1. So we want to prove that what our result is 95% certain of being different than 1. So if 1 is within this range, we can't say with 95% certainty that the real value for 1.4 is different than 1, because we're not 95% sure that it can't be 1. Since in this particular case, I found that the confidence interval excluded 1, didn't contain 1, now we can say with 95% certainty that this 1.4, which is our point estimate, is indeed 95% certain of not being 1 because it doesn't contain 1. Is everybody comfortable with that at this point? No, it didn't ask for a confidence, and the test didn't ask for a confidence interval. If you're gonna, if in the test itself, That's a good question. I don't think there's going to be an easy way for you to calculate confidence interval using only Excel, using anything that you have on the test itself in a reasonable amount of time. So if you're going to get a confidence interval question, it'll come up in a table where you'll have to be locating it and understanding it from a table, or you'd have to have SPSS or something like that in order to calculate it. In fact, at some point here, maybe we're going to calculate it as well. Okay, so that's our odds ratio, that's our relative risk. Now, although we're not going to be able to calculate our confidence interval, we have another way that we're going to be able to figure out whether or not we can reject the idea that there's no difference between wearing a helmet and not wearing a helmet. Okay, you guys know what that's going to be next. I estimated the confidence interval. I didn't actually calculate it. Okay, so we're going to actually go ahead, though, and find another way of examining this data that allows us, without doing the confidence interval calculation, to determine whether there is a difference between wearing a helmet and not wearing a helmet in terms of the exposure for head injury. Okay, and that's going to be, we're going to calculate our chi-square value. Okay, so now these are our observed values, and these are our expected values. And we know that when we calculate chi-square, right, I'm going to move this over here. The way we calculate chi-square is we calculate the difference between the observed values and the expected values, and then we square that, and we divide it by the expected values. So I'm going to go ahead and do that. That's going to be equal to 24 minus 20.4, our expected value. Okay, I'm going to square that. Or just, in other words, just multiply it by itself. And I'm going to divide it by our expected value, which is 20.4. Okay, there's our formula. Really, in real life, that's just 24 minus 20.4 times 24 minus 20.4 over 20.4. And I wind up with a value of 0.6474 and so on. I'm not going to bother to round that because I need that in my calculation. If I round that, and we're doing this on paper and rounded that at this point, I might lose some of this information and I might get a different result than I might have gotten if I didn't round this. I wait for the very end to round stuff. Okay, fortunately, again, Excel always preserves that for me anyway. Okay, so now rather, my next calculation down here is going to be 19 minus 22.6 squared divided by 22.6. I can do that manually, or I can just ask Excel to fill that formula down for me. Okay, and that's what it calculates for that cell. My next two cells are these two cells over here. Since I'm doing the same calculation right next to them, I can just go ahead and copy that left. It'll copy that formula for me to the left, right, excuse me. And there are the calculations that I have, my total for each cell. So now I'm going to add those together to get my chi-square value. Okay, that's going to be, I love when I get a call coming in. The caller ID is important. Obviously, if the caller ID is important, it's not important. So I'm going to add these together. Oops, excuse me. Parentheses. I'm going to add them all together, and my chi-square value is equal to 1.59. Okay, anybody remember what the critical value for chi-square is for a 2x2 table? First of all, number of degrees of freedom. Degrees of freedom, that's going to be equal to, we know, I'm not going to bug you for that, that's going to be equal to 1 because it's 2 rows and 2 columns. 2 minus 1 is 1, 2 minus 1 is 1, so it's rows minus 1 times columns minus 1. That's just equal to 1. So 2 degrees of freedom. Anybody know what the critical value? I could look that up on a table, right? Okay, 3.84, good. Excellent. Critical value is 3.84. So now what this is telling me is that if I were to draw my chi-square distribution, that I am not far enough out to the right. I don't have a big enough chi-square value to say that the chances of there being no difference between these two tables and getting a value that high is less than 5%. I'm not far enough out there to say that. So in this particular case, I fail to reject my null hypothesis. Now, to backtrack to something that we really should have started with when we began this whole thing, what's our null hypothesis? Well, our null hypothesis is that there's no association between wearing a helmet and the likelihood of having a head injury. Okay, and the alternative hypothesis is that there is an association. No association would imply a risk of 1. No association would imply an odds ratio of 1. And no association would imply a chi-square value of less than 3.84. So we fail to reject that null hypothesis. So we can't adopt our alternative hypothesis that there is an association. Okay, so that's where we are with that. Okay, so now, of course, if they ask you for a different level of a different critical value for chi-square, you could then say, look it up on the table, and you would have to exceed a different number. If it's instead of a 2x2 table, it's a 3x6 table, you'd have a different number of degrees of freedom, so you'd have to look up on the chi-square table what the critical value would be for that. Incidentally, there is a way 2 equals chi test. There's a way that once you've calculated your observed values and your expected values in Excel, you can actually use chi-test, comma. If you notice down here, it says actual range and expected range with a comma between them. Here's our expected range. Okay, and I get a value of 0.207. That is actually not chi-square. That's the p-value associated with that chi-square of 1.59. Okay, so the probability of being wrong if you reject your null hypothesis, where your alpha error is equal to 0.2, okay, which is not less than 0.05, so we get really the same result. And if you want to just confirm that, chi inverse, okay, changes the probability to p-value, comma, for 1 degree of freedom, back into a chi-square value. So it's really the same chi. It's really that you've checked that p-value really is represented by that chi-square value, in case you want to do that. So I think we've beaten this to death, right? So let's move on to the next problem. Okay, so next problem involves regression. Okay, and it involved, I think we used that World 95 for the lab exam. For this, I'm going to use, I got to move things around a little bit here so I can get to it. I'm going to use an example that's a little bit different. Okay, and both of these examples are a little less satisfying because we don't reject it. I don't think we reject the null hypothesis in either one of them, but that's okay. I mean, that's why you do it. Okay, in this particular example, what we have is the result. I guess I opened that a couple of times. What we have is the result of a series of 25 eBay auctions. This is from the text. This is from Agresti, one of the data sets. I don't remember exactly how they used it, but I'm going to make up my own version of it. Let's say we're selling an object repeatedly on eBay. Each time we sell it, we list it for a different price. And we're interested in knowing whether the price we list it for influences the number of bids that we get for the object. Okay, so I'm saying, gee, is there a relationship between the listing price and the number of bids that it generates? So first thing I want to do, this is a numerical variable. This is a numerical variable. So I can it might be of interest to me to predict whether or not there's a correlation between price and the number of bids. Okay, and I can just go up to analyze. I can directly go and do a correlation. I might even want to see if it's predictive. I might want to do a regression. But before I do anything, I want to take a look at what this looks like on a graph. So I'm going to do a scatter dot and simple scatter dot. And I'm going to say, well, since I'm doing correlation, it really doesn't matter which one I put in X and Y axis, but I just want to stay consistent. Basically, what I'm saying is that the price determines the number of bids that I get. So I'm going to put the price as the predictor variable or independent variable on the X axis, and I'm going to put the number of bids generated as the dependent variable or the outcome variable on the y-axis. Okay, y is equal to some function of x. So this makes this independent. That makes y is predicted by x, makes that the dependent variable. But if you just keep in mind, remember, a lot of times you call this dependent or predictor, and this one you call, independent or predictor, and this one you call outcome or dependent variable. Okay, so I'm going to say okay, and let's see what this scatter plot looks like. Here's a scatter plot. Some of you may have already discovered a trick that if I double click into this, I can do all sorts of things like label these points and so on and so forth. And one of the tricks I can do is if I hover over the add fit line of total, I can click on that and it automatically will add a linear regression line. It'll actually predict the regression, draw the best fit line. Okay, so now one of the things I see here is, gee, these values, this value particularly is really far away from all the other values, kind of an outlier. Maybe that's an outlier. I may want to go back and take a look at that. I also note that in general, as the listing price gets higher, it attracts fewer bids. Okay, so it looks to me like there may be a relationship here. Do you guys agree that there looks to be a relationship here? Yeah, I think so, right? I don't know how strong that relationship is, and we're going to try and quantify that relationship right now. You guys may remember that I think we actually did a couple of calculations of correlation either in class or on one of the homeworks or something like that. I seem to remember we had an Excel sheet where we did a simple one, but we're going to get SPSS is going to do it for us here. So we're going to go to correlate bivariate. Now, correlation doesn't really care which one you put first. So I'm going to put price and bids. Notice that there's no dependent, independent. It's just going to calculate Pearson's chi-square value. You remember that from the differences in means and so on and so forth, and those four columns that we use. Okay, in this case, it finds that the correlation value is, let's see, well, it's negative 0.310. Okay, well, we know that, first of all, the fact that it's negative suggests that as one variable goes up, the price goes up, the other variable goes down, the number of bids go down. And that agrees with what we see in the graph. But as far as the value of the correlation, well, let's take a look at it. 0.31. Well, we know 0 is no correlation at all. And 1 is a very strong correlation in either direction, plus or minus. 0.31 is not a very strong correlation, right? So I'm going to continue to use this example, but even though it appears that there seems to be somewhat of a correlation, we don't have a really very strong correlation. So let's go back and let's actually take a look at what we might be able to do with this. And let me just see what questions we've answered, what we haven't answered. Okay, we constructed a scatter plot and we want to paste it in there. I'm going to actually go ahead and do that. So I'm going to copy. I use Control C to copy, and I'm going to paste. Except I'm going to say paste special. In this case, paste and paste special are going to be the same thing because I just copied a picture out of an Excel output. So it's only going to give me the option of pasting a picture. Later on, it may give us a different option. Pasting it actually keeps it, using paste special and choosing a picture or a bitmap or JPEG as the sort, as the choice. Actually, number one, keeps it within the margins. And number two, allows me to resize it a little bit easier than if I didn't do that. Okay, and if I want to center, I gotta highlight the whole row actually, and it'll allow me to center it if I want to, and so on and so forth. Okay, so at any rate, that's what our scatter plot looks like. It's nice. We think there's a correlation. We're not very satisfied with the how strong the correlation is, but we're going to go ahead and go on. We've already answered this question. Are there any outliers? Well, gee, it did look like there was an outlier, right? That value right there looked like an outlier. Well, what value is that? There are ways to turn on labeling when you do the charting. I'm not going to bother with that. For now, I'm just going to relate these two values. So in fact, this particular value was the highest number of bids, which was about, I don't know, 32. So I can go back to my data set And let's see, 32 is, where's the value for 32? Here we go. Number that when we listed it for $225, we got an unusually high number of bids, right? And that we might want to examine that. Maybe we'll go back and take a look at what happened during the bidding there. Maybe there was, if you've been on eBay, maybe one guy kept adding $1 to his bid or something like that, and maybe I might have a reason for believing that that is not representative of what the real relationship is, and I might want to eliminate that from my data set. Okay, eliminating that outlier from my data set is going to give us a better correlation. We don't have that extra value there changing our correlation, or maybe these three or something like that. The rest of them seem much closer to that straight line. So that outlier is uh, is causing some problems with our outcome. Not only that, but one of the other things I want to keep an eye on is when these outliers are in the middle here, right? They tend to shift this line up or down, but they don't tend to change the slope of the line very much. But if we have an outlier over here and we have an outlier over here, right? Well, those outliers that are at the extremes of the independent variable, like at the left or the right, they have a tendency to say, take this line and pull it, change the slope of this line. Slope of this line is very important to us. The slope of this line tells us what the relationship is between our independent variable and our dependent variable, right? The height of this line, or where this line exactly is, that's not really that important to us because we know that's going to be an intercept involved and so on and so forth. But we're really concerned about the slope, how one variable impacts the other variable. So we're more concerned about outliers on the outside here. You can kind of almost think of it as a teeter totter. The further out you are on the teeter totter, the more influence you're going to have on the guy on the other end, right? You might want to keep that in mind when you discuss or observe outliers. So now I'm going to go ahead and I'm going to go and do some regression analysis on this. Regression analysis, the difference here is that with regression analysis, we want to use this relationship so that we can predict outcomes. So we can evaluate and predict outcomes. So I'm going to choose linear regression. I'm only dealing with two variables, so it's not a multiple regression. It's a simple linear regression. My dependent variable, the one that I'm predicting is going to be changed, is bids, number of bids, and my independent variable, the one that I think is causing the number of bids to change, is going to be price. Okay, so now I'm going to go ahead and just say calculate it. Okay, and let's see what we wind up with. First thing, we repeated the R value calculation. Notice it didn't bother to put the sign in here, negative. It was actually negative 0.31 because it's really determining that R value so it can calculate a predictor, R squared. Okay, so now R squared is equal to, say, 0.1, or just say it's 10%, or 0.1. Okay, what does that tell us about the relationship between the quantitative relationship between the price we listed at and the number of bids that we get? Okay, anybody have an opinion about that being 0.1? Okay, sorry to wake you guys up. Okay, thank you. Well, what that tells us is that the variability, good, thank you, Bill. The variability in the number of bids, only 10% of that variability is predicted by the bid price that we listed it at. The rest could be predicted by some other factors. The day of the week that we listed it, the size of the picture that we put in there, the number of pictures that we put in there, the description that we gave it, so on and so forth. Right? So 90% of the difference in of the bid number of bids is predicted by some other variable that we don't know now. So this is not a very good predictor. But we're going to plow ahead and see what we know about this anyway. Okay? Well, next we take a look at the significance of this result. Can we rely on this result to be statistically significant? And typically we're going to look over here to our ANOVA table and we're going to see 0.132, and this says that basically, well, there's more than a 5% chance that we'd be wrong if we predicted any correlation between the number of bids and the listing price that we listed it at, right? So this isn't even really a statistical result. Nonetheless, I'm going to plow ahead and we're going to go ahead and use this anyway. But at this point, we might question our results or go back and try and take a look at another way to do this study. So now finally, we go down to our coefficients table. Our coefficients table now tells us, gives us values that we can use to write a formula that predicts the outcome variable from the independent variable. Okay, so, and the way it does it is it gives us the y-intercept, which is called constant in this case, and it gives us the slope of the line. It describes it as the independent variable, price, determining the number of bids. Okay, so this basically tells us for every $100, for every excuse me, I'll rephrase that. For every $10 that that we go up in price, that the number of bids will be reduced by 1.4. Okay, now that's a little bit hard to visualize here, but let's put the formula into Excel so that we can work with it and examine it a little bit more closely. Okay, I'm going to move this up. Okay, so y is going to be equal to my intercept, A, and bx. My formula, y is going to be equal to where it crosses the y-intercept plus my slope times my independent variable. Y is equal to, if you're all math days, y is equal to mx plus b, this b being the intercept. In this case, y is equal to a in slope times this, the y-intercept and the slope times the independent variable, or x. Okay, so in our case, y is the number of bids, right? That's what we defined as our outcome variable. Is going to be equal to a constant. The constant is, I'm going to round it off to 40 just to make it easy for us to work, times b times x, or the slope times x, or in other words, minus 0.142 times x. And what is x? Oops, I should have put a space in front of here. And what is x? Well, x is actually the listing price. So I'm going to change that to listing price. So if I were to write this as a formula, let me insert a column here. I'll insert a column here. So if I were to write this out as a formula, this is kind of what it would look like. Number of bids is equal to 40 plus, let me get rid of that equal sign there, put space instead. 40 plus the slope times x. In this case, the slope is a negative number, so 40 minus 0.142 times the listing price. Everybody comfortable with that? See how I got that formula? Should I pull out the graphics pad and write it down? Right? It's pretty clear, right? That's how that formula, that's how we derived that formula. Okay, so now there's a number of things that this tells us. One thing that it tells us is that for every dollar we go up in the listing price, we're adding, or we're subtracting the a 1.4 0.14 bids from the number of bids that we would expect to get. If I go up $10 in the listing price, 10 times negative 0.14 is going to be negative 1.4. So it's going to be 40 minus 1.4. I'm going down 1.4 bids. If I increase the listing price by $100, I would expect it to reduce the number of bids by 14 bids. Okay, and so on and so forth. So this is going to describe our relationship. Okay, so now there's a number of things that I can do with this. One of the things that I can do with this is that I can say, well, gee, how many bids should I expect if I list this item? Let me see if I can't see. Let me see something that I don't have here. I want to be within this range. Let's see, 178, about 180. I don't see 180 in there. Okay. How many bids would I expect if I list this item for $180? Okay, so my number of bids is going to be equal to 40. It's going to be equal to 40 minus 1.42, excuse me, minus 0.142 times 180. Okay, so now let me see if I got that right. 40 minus 0.0142 times 180. Excel's going to, I'm not going to bother with parentheses because Excel is going to do the multiplication first and then the subtraction, which is the way I want it anyway. So I think I can get away with it. I would expect 14.44 bids. Okay, so now this is the number of bids that I would expect. So I've used this to take a value that I don't actually have in this population. I don't, in my sample, I don't have, I never listed it for $180. So I use that regression formula to predict what the number of bids I would have drawn would have been had I listed it at that particular price. On the other hand, I can test this regression equation. I can say to myself, well, gee, let's take a look at a particular value, 200. Okay, I'm gonna substitute 200 in this formula for that 180. The formula predicts that the number of bids that I would get is 11.6. Okay, well, in this case, I have an actual value an actual time that I listed it for 200. Okay, and if I go back here, when I listed it for 200, I drew 18 bids, right? So the value I predicted was 11.6 bids. The value I actually got was 18 bids, okay? Now, the difference between the number of bids that the predicted value of bids and the actual bids is going to be my residual value. Okay, it's going to be the difference between these two. Okay, measures actually would have been positive, I think. I think normally you do the actual value minus the predicted value. So, but the difference is 6.4 bids. Actually, I can actually calculate residual values for all of these subjects. I'm going to go back here, regression, linear. I'm going to go into let's see, save. I'm going to tell it, give me the predicted values and apply the formula that just calculated, and also give me the residuals. Click continue, say OK. And when I come back, I get the same result there. But when I come back, it gives me all of these different values, including the one for 200, where as we predicted, our residual value was 6.4. The difference is 6.4 bids. Okay, now one of the things we're always concerned about is whether these residual values are normally distributed. In other words, there's not some pattern or there's not some other reason for each one of these to be different from the predicted value other than just random chance. Okay, and so we would be looking for that. We really didn't get into that too much, so I'm not going to press that here. But that's one of the things that you might want to remember about residual values is that you would expect them to be randomly distributed or normally distributed. You wouldn't expect them to have a particular pattern like the ones that the higher number of the higher listing prices you would be underestimating all the time, and the lower listing prices you would be overestimating all the time, or something like that. Or in the middle, you'd be overestimating in the other ends, and at the opposite ends, you'd always be underestimating. Okay, we don't want to see a particular pattern there. We want it to be really kind of a random a distribution of residual values. Okay. 11.6. Where did I get 11.6? I'm not sure where that came from. 11.6. 6.4. Right? We agree? Okay. So let's go back to our document and see what we got asked, just to make sure we covered all the bases. Okay, are there any outliers? Well, we kind of in this particular example, we figured that might possibly be an outlier, and we identified which value it was. Perform a regression. What is our null hypothesis here? Right? Anybody want to come up with a null hypothesis for this relationship? Okay. Well, basically, it's that that there's no relationship, no association between the number of bids, the asking price, and the number of bids. So starting price and number of bids. The alternative is that there is a relationship. I'm going to leave the details for or maybe we'll get to it tomorrow night. Details about what are our assumptions when we do correlate. We didn't get really discuss that too much right now. Chi-square, odds ratio, relative risk. What are our assumptions? You can probably find those pretty quickly in the book or in the one of the PowerPoint slides. What are our assumptions for correlation and regression? And one other thing, just so you remember, just keep in mind, remember we had a rule about um, uh, uh, chi-square values when we do our predicted and observed values, that we want the values in the expected values. Every cell in the expected values should be at least 5 or greater, right? So you might want to keep that up in mind in case it were that curveball would be thrown, say on Monday. It's not in this what we're doing right now, but if that came up on Monday's test. Okay, so we want to paste we're asked to paste in the table describes the model in SPSS. Let's go to SPSS and get our output. Where is it? There it is. Nope, that's this. Wrong one. I don't want that either. Did I close SPSS? I think I might have closed it. Nope, there it is. And let's go to our output. Okay, here's our model table with our correlation, our R value and R square value. I'm going to highlight it, go up here and say copy. Then I'm going to go back to my Word document. I'm going to say paste. If I say paste at this stage, not much of a problem, right? That worked out pretty well, so I'm not going to worry about that. So now it asks us a few questions about it. I think we answered most of those questions, except for us, it's the variables are different. Now let's go to the table that's described as coefficients. I'm going to click on that, copy. Let's see if I get away with it again. And paste. Well, notice that I've gone outside the margins here. And it's kind of tough. If you look up here, the tabs and so on, you can adjust the tabs and change the table size, but it gets a little wanky, right? The nice thing about this is that I can go in there and I can actually edit these things. I can change the color of something and so on and so forth. The bad thing is it's very difficult to work with within a Word document. So if it's still paste, it's still in my clipboard. If instead of paste, I had said paste special, you would have given me the option to put it in as formatted text, unformatted text, picture, style text. This time I'm going to choose picture. And if I click it in as a picture, it automatically confines the table to the size of the page that I can display it on. And I can still, if I want, very easily resize it, or even more easily resize it, or move it around if I need to move it around. So if I'm not expecting to edit these numbers or do anything, if I edited them instead in SPSS, very often SPSS, you double click into a table, gives you the opportunity to edit it. Okay, if I was happy with the table as it was produced in SPSS, sometimes it's easier just to paste it in as a picture. Okay, so I think we beat that. We took care of this for now, and we're going to be covering some more material tomorrow night. And try and send me, let me just make sure the missing values, formula, predict based on the model. We took a number, we look to see what it was going to, what the real value is. The data file indicates the actual value is so-and-so, and resuming, I think we pretty much covered all that, right? Except you got your own data set to work with. So make sure you work with the right data set in case you do. Okay, I'm going to minimize that rather than close it. Okay, any quick questions now or things you want to cover tomorrow night? All of the answer to the question, what should be greater than 5, is that if I look at my chi-square values, oops, let me get to Excel. If I look at my tables, my observed values and my expected values that I used to calculate chi-square, I need for my expected values to always be greater than 5. Because just thinking about it, if I have 100 people here, but I only had 2 people, if the rate was so low that I only had 2 people that came in that were wearing helmets, it would be hard to make a good statistical judgment on how important this data is, right? So we want to make sure that in the expected values table that all of these values have at least 5 individuals that are represented in those boxes. Okay, it doesn't matter, not so important in the observed values, because in fact, if you have very few here, if no one wearing a helmet was injured, that would be a pretty significant find for us, wouldn't it? Versus we expected 22, for instance, right? So we're not so interested in the actual value being greater than 5, but we need, for statistical purposes, for all the values in the expected value table to be greater than 5. That's kind of a curveball that shows up on tests every once in a while, maybe in a multiple choice question or something like that. But just so you're aware of it, okay? And again, keep in mind that, especially tomorrow night, or you really should bring it up on the lab exam as well. You mentioned the lab exam as well. But when you do these kind of analyses, you're always considering in the background, number one, what's your null and alternative hypothesis? Number two, what are your assumptions when you perform a particular test? Okay. You should know what the R. No, I don't think you need to worry about adjusted R square value. I don't think it's going to come up. The minus 1.42 came from the table. Remember the, let me see, let me go back to the output here from SPSS. Let me get my output. Here's the output. Okay, the minus 1.42 came from, that's our slope. Remember, the coefficients gives us the numbers that we need for our formula that predicts the relationship, in this case, between the number of bids and the price. So the number of bids is equal to 39.94 plus negative 0.142 times the price. Okay, so this gives us our formula for that equation. Okay, that's our slope, or the number we're multiplying the independent variable price by, or whatever it happens to be. And this is our y-intercept, or the number that we're adding to that formula. I think I might still have, do I still have that? Yeah, number of bids is equal to, I rounded to 40, right? Minus 1.42 times the listing price. Okay. Okie doke. The outlier question is not on our exam. Isn't it? Isn't the outlier thing on the lab exam? Isn't there an outlier question? Unless it got left out. I don't know. I'll just answer what's on there. Okay, guys. So let's call it a morning. Try and enjoy the rest of the weekend. Looks like it's going to be a couple of pretty good days, and get in a little bit of study. And I'll see you guys tomorrow night. Yeah. Well,